Hello, my name is Tim Harrison and I'm a chemist here at Bristol Chem Labs, which is in the School of Chemistry, the University of Bristol, and we're in one of our large lecture theatres filming this talk, which is Gases in the Air, a lecture demonstration I've been privileged to give over the last 17 years in about 28 countries on 5 continents. And what we're going to do here is look at the main gases in the air that are around us. Now everybody looking at this will know that the air is a mixture of gases. The air itself is not just one single gas as the ancient Greeks thought, it's a whole mixture of gases. And I'm just going to give you 15 seconds to see if you can name as many gases in the air as possible. Okay, so what you would likely to have come across, bearing in mind I've done this with lots of groups before, are the main gases in the air. So I guess you would have mentioned nitrogen gas, you would have definitely mentioned oxygen gas, probably carbon dioxide, some of you will have mentioned water vapour, but there's lots of other gases in the air. Some that you may have come across before are things like sulfur dioxide, carbon monoxide, and if you were looking behind me, as you were making a list of these gases, you might have even mentioned helium gas. But there are thousands of gases in the air, some of which you will have never heard of. But we'll concentrate this talk on the main gases that are in the air. Now, while we've got the blues here, let's actually talk about these particular gases. The gases in both these balloons are what we refer to as low-density gases. If they are full of a gas that allows the weight of the balloon and the weight of the string to rise, it's a low-density gas. And you might have some ideas about what those gases are. One or two of you might be thinking that the gas is air. Well, let's put that straight to start with. If I blow this up, granted, I'm using the air coming out of my lungs, which is nearly the same as the air going into my lungs. This is a balloon now full of air, and if air was a low-density gas, this balloon should rise. And obviously it doesn't. So it can't be air that's in these balloons. Some of you will have known from various parties that you have a gas called helium that is a party balloon gas. And that's what I've got in that balloon to my right. This is helium gas. Helium is a relatively safe gas, otherwise they wouldn't give it to small children at parties. It's a gas that is not poisonous, it's not toxic, it's a gas that is non-flammable. In other words, you can't make it explode. And in a moment or two I'm going to show you that that won't explode by trying to set fire to the gas inside the balloon. Before I do that, let's consider this balloon. This is also a lighter than air gas. This is the gas hydrogen. Now hydrogen and helium make up 99.9% of the visible universe, hydrogen being most of that. In our planet, in our atmosphere on planet Earth, less than 1 part per billion is either helium gas or hydrogen gas, and a billion is 1,000 million. So if you were to breathe in 1,000 million times, one breath would be hydrogen, one breath would be helium. Hydrogen, unlike helium, is not a safe gas. It's a gas that's explosive. And I'm going to set fire to that balloon, or the gas that's in that balloon, to show you. So I'll just light up my burner. And I've got a measuring rule here with some wooden spills on the end so I don't have to be too close to the balloons. We'll have a look at the helium gas to start with. That merely bursts like an air-filled balloon would burst. As we have an air-filled balloon here, let's just show you that. Not quite the same noise, but you can see that neither case was there a flame coming out. Let's have a look at hydrogen. If you were in my lecture theatre at this point, you'd now be putting your hands over your ears. Let's see what the difference is. Let's see if we can make some observations for hydrogen. As you can see, and as you can probably hear, hydrogen is an explosive gas. It burns really well. That's the reason that we use helium for balloons for parties and not hydrogen for balloons for parties. Let's put this out of the way for a moment. Let's concentrate on the main gases in the air. Let's concentrate on nitrogen. If you were to breathe in and out 5 times, 4 breaths out of 5 would be the gas nitrogen. Now that's an approximation, that's a rough estimate. If you want to have a better and more precise answer to what is the part that nitrogen plays in the air, what percentage, what fraction, it's 78 parts out of 100, it's 78%. If you look about you, most of the gas that's in the air in where you are is nitrogen. And if you put your science brains on and make observations, you will notice that the nitrogen gas has no colour. If you sniff the air, anything you're smelling can't be nitrogen, so it has no smell. And if you taste the air, and you don't need to lick the air to taste it, there's already air in your mouth, it has no taste. So in science terms, because we have no colour, we say it's colourless. Now it also happens to be clear, see-through and transparent. But the lack of colour means it's colourless. Yellow glass in a church window is clear, see-through or transparent, but yellow glass is yellow. Seeing through something doesn't tell you its colour. Nitrogen gas is colourless, it has no smell, it's odourless. It has no taste, it's tasteless. It's pretty boring. Let's see if we can explode the nitrogen gas that's in the air. Well, the entire atmosphere of planet Earth did not explode at that point, so that can suggest that nitrogen does not want to burn. Nitrogen is a boring gas. And because it's a boring gas, it doesn't mean to say it's useless. We can use nitrogen to make this stuff. Some of you will actually know the correct names for these. If you think this is polystyrene, well, I'm afraid you're wrong, because polystyrene is a hard plastic. This is correctly called polystyrene foam, or even expanded polystyrene. Our American cousins and others actually call it styrofoam. This is polystyrene that has had a gas put into it to turn it into a foam. And these days, the gases that tend to be used are nitrogen. Now, we can get the nitrogen out of the expanded polystyrene very easily. What we need is the active ingredient in nail varnish remover, a chemical called acetone, and a beaker. Now, acetone is what we call a solvent. In nail varnish remover, there is a small amount of acetone and a large amount of water, but it's the acetone that clears the nail varnish, the nail polish off people's nails. Here is a nice big piece of polystyrene foam. Let's just see what happens when we put that into the beaker. If you look closely at the interface where the foam is hitting the liquid, you can see the gas bubbles being released from the foam. Now, the polystyrene foam isn't dissolving, and it's certainly not melting. There's no heat involved. It's not dissolving because we can still see the polystyrene that's in the bottom. The polystyrene has simply had its structure changed by the solvent, allowing the gas to come out. Now, if you want to know how much gas is in polystyrene foam, let's do a quick experiment here. We've got some polystyrene packing pieces here, 1 litre of them. They happen to be green. I don't know why they're green. It'll make it easier for you to see, I suggest. If I use the same solvent, the same nail varnish remover ingredient, and put that into the litre bottle, you can see that there's very, very little polystyrene in a litre of polystyrene packing pieces. And the beauty about having this bottle is I can screw the lid on and stop the smell getting up my nose. Let's just get rid of this. So nitrogen gas, fairly boring, even though it's got a few uses. But let's consider what happens to any gas if we allow it to cool down. So we take some nitrogen gas and we cool it and cool it and cool it. What will it turn into? Well, the answer, of course, depends on how much you cool it. If you cool it at absolute load, it will become a solid. But before it gets to a solid, it will become a liquid. Now, in science, we say that when a gas is cooled down and it turns into a liquid, we say the gas condenses. And when the liquid is cooled further and further and further down, and we remove more and more heat energy from the liquid, we say that the liquid freezes into a solid. But I want to talk about liquid nitrogen. Liquid nitrogen exists. If we get nitrogen gas and cool it down to a temperature of only minus 196 degrees centigrade, it will condense into liquid nitrogen. Now, minus 196 degrees centigrade is 220 degrees colder than the air in this lecture theatre. It would make it one of the 5 coldest liquids in the universe. And as such, it's potentially very, very hazardous, or it can be hazardous if you don't know what you're doing. We have to use special equipment to handle the material. This is a flask that will allow me to pick up a solution, a liquid of nitrogen, liquid nitrogen. This is a flask that has an outer skin and an inner skin, and between those two pieces of glass used to be air, and that air has been sucked out and then sealed off, so there's nothing between the two layers, and nothing in science is a vacuum. This particular flask was invented by a Scottish engineer by the name of James Dewar, so in his honour we call these things Dewar flasks, and it's an expensive piece of equipment. The liquid nitrogen I have is in here. This is another Dewar flask. This is liquid nitrogen in a Dewar flask. This is a 500-pound container. This will keep my liquid nitrogen cold for up to 5 days. It will keep my coffee boiling hot for 5 days because it doesn't let heat in or out. Look how thick the insulation is to stop heat passing through the lid. Let's have a look at this liquid nitrogen. You are looking at nitrogen in the act of boiling. Let's get the term boiling sorted out. Boiling is when a liquid becomes a gas. Boiling doesn't mean hot. A lot of people in everyday life use the word boiling to describe the weather in the summer. You know, if you're going outside in August, your mum and dad might say, take a bottle of water with you because it's going to be boiling outside. Well, it won't be boiling outside. If it was boiling outside, everything would turn to gas. Boiling does not mean hot. This is liquid nitrogen is boiling at a temperature of minus 196 degrees centigrade. It's boiling, but it is certainly not hot, being one of the 5 coldest liquids in the universe. And for the little ones amongst you, let's just consider how cold that is. You might think your fridge is cold. Your fridge operates at a temperature which is about 20 degrees colder than your kitchen. You might have a deep freeze in your kitchen. That'll operate at between 40 and 45 degrees colder than your kitchen. If you were silly enough to be down the South Pole midnight, midwinter looking for polar bears, well, you'd be silly for 2 reasons. Reason number 1, the polar bears live in the North Pole. And the second reason is it's about 105 degrees colder. It's very, very cold down the South Pole. This is 220 degrees colder than the South Pole. Very cold indeed. Let's concentrate on some of the action that properties have in cold liquids. Let's look at the material properties in cold liquid. We've got a number of things that we could stick into liquid nitrogen, including this. This is a piece of rubber tubing. So it's made out of rubber and it's tubing because there's a hole running down the middle. This has been in this lecture theatre for at least 3 days. So we know that this tubing is at room temperature. Room temperature happens to be 220 degrees hotter than that liquid. And if we put the tubing in, this is what happens. We can get the liquid to boil and shoot out liquid droplets. We're making nitrogen rain. And then it stops. Now the reason it stops is the end that's in the liquid has now given away its heat energy. It's caused some of the liquid to boil. That in turn pushes out any unsuspecting droplets of liquid that get in the way. And it only stops when the bottom end of the tubing is the same temperature as the liquid. This end is now dangerously cold. This is so cold, if I was stupid enough to put my hands over it, in 5 seconds, my flesh would freeze to its surface, and when I pull my hands away, bits of my dead flesh will be left on the pipework. It's a cold temperature danger, something we refer to as a cryohazard. And you might just notice that the end of the tubing is changing colour. Colour change usually signifies chemical change. You may not know about some chemical changes. Let's give some examples. I've got 2 chemicals here dissolved in water, so they are solutions. A solution is when you dissolve things like salt in water. It's a salt water solution. The colour of this solution, well, it doesn't have one. It's colourless. The second solution is also colourless, but when I add the 2 together, there's a chemical change. And sometimes when you get chemical changes, things like this happen. Now that will stay yellow from now until the end of time. That's an example of an irreversible chemical change. It will stay yellow forever. Unlike the chemicals I have in these bottles. These may look fairly colourless, slightly yellow I guess, it's more like urine. However, when you shake them up, I can bring about a chemical change. I can put the oxygen that's in the air in the top of the bottle into the chemical mixture in the bottom, and it brings about a chemical change, and we can see that because of the colour. But unlike the yellow, which stays yellow forever, in about 5 to 10 minutes, these 2 will go back urine colour again. These are reversible chemical changes. The white stuff on the end of this tubing is nothing to do with chemical change. Now, while I've been talking, this has been warming up. It's now safe for me to show you this. If I can put my fingers down, I can pull off this surface white powder. And of course, you've worked out what this is already. This is frost, it's snow, it's ice, it's solid water. Now think about where that comes from. Let's just cool down the tubing again. Water vapour in the air that you can't normally see, watch, water vapour coming out of my lungs you can't see, is being cooled down and condensed to billions of droplets of liquid water. And we can do this large by breathing into the liquid nitrogen. Some of those droplets of liquid water, the bit that we're looking and seeing as cloud, are sticking to the surface of the tubing and becoming solid water. The liquid water has been made by condensation and is becoming ice, frost, snow, solid water by freezing as it cools down further. That's a physical property change, not a chemical property change. And here's some more physical property changes. The warm end of this tubing is squidgy. Okay, we call that being malleable if you want to give it a science term. If I try the colder end, you see I can't bend it. I can bend it at the warm end immediately above the cold end, but I've changed the physical characteristics. I've changed the physical properties. And here's another one. Listen to warm rubber. Listen to cold rubber. A a change in sound-making properties, a change in sonorous properties, another physical change. If you just look at my original samples here, you see they've gone back urine colour again. This is definitely reversible chemistry. Let's leave that over there for a moment. You might be wondering why I'm not wearing safety gloves when I'm doing these experiments. You've all seen safety gloves. Your doctors, dentists and nurses wear safety gloves. And these safety gloves are actually made out of latex rubber. They are really rubber gloves. There are lots of other materials that people use and still call rubber gloves, but they're not made of rubber. This very stretchy at room temperature. Chemists tend to wear them over their skin to keep their skin away from the more hazardous chemicals. I'm not wearing one here, and I'm going to show you why. Let's put a glove in liquid nitrogen for a few seconds. Now please notice that my fingers are not in the liquid. If I left my fingers in liquid nitrogen for just 5 seconds, my flesh would freeze through to the bone. I could then snap my fingers off. I don't want to do that. Fortunately, the rubber floats. Why am I not bothering to wear one as a glove? At cold temperatures, the rubber becomes rigid, not flexible, and so it would be useless as a glove. If I just warm that up for a moment, what we'll notice that when it is warm, and it warms up very quickly because it's so thin, we get the flexibility there, the fact we can stretch the glove again. So that's a reversible physical change. These two, I will remind you, that one hasn't quite gone yet, are reversible chemical changes. Let's do a couple of other experiments while I tidy this up. Let's see what happens with this balloon, rather ugly looking balloon. What happens if I put this into liquid nitrogen? You might want to make some predictions before I do this. There's only 3 possibilities. If I'm going to cool this down, either the balloon size will increase, the balloon size will decrease, or the balloon size will stay the same. I suppose there is a possibility if I do the experiment incorrectly, I might break the balloon. But if that happens, we'll just get a spare balloon out and show you again. So let's put it in there. Now, I have to push the air from the top into the bottom because the only place the air is cooling down is in the bottom of the dewar. So I'm going to push it and push it and push it, and you can probably see already what's happening. There we are. That's curious. Let's see what happens when I warm it up. Use the heat out of my hands here. Well, it's getting back into shape. Seems to have a very thin neck at the moment. So when the air inside the balloon is cold, the volume seems to shrink, and when the air gets warmer, it seems to get bigger. There's 2 reasons we could use to explain why that is. Either when the air in the balloon is cold, the air particles get smaller, or when the air in the balloon gets cold, the air particles huddle closer together. And when it gets bigger again, is it because the particles get bigger, or do the particles just move further apart? Is it size? Is it distance? Well, let's find out why. Here I've got 2 thick bits of glassware. There's a balloon attached to a little spout. Watch. Oh, that was rather unusual. I'm going to do the experiment twice because scientists love repeats. So I'm going to imagine I can pour in and guesstimate 35 millilitres of liquid nitrogen. They can't use a measuring cylinder if the measuring cylinder is so warm that the liquid nitrogen boils as soon as you hit it. You'll never be able to measure it correctly. Let's do something stupid. Let's seal a system producing a gas. Make a prediction about what you think is going to happen and see if you can work out why. Well, that was a very quick piece of experiment. Let's see what happens on the left-hand side. Remember, to start with, the glassware was warm. The liquid could take the heat and become a gas. The liquid is boiling into the glassware, and that gas, the nitrogen gas that's produced, has to go somewhere. Eventually the balloon gets filled up, and the balloon can't take the pressure anymore, so the balloon explodes. Now, you can probably see it's still producing cold nitrogen gas coming out of the side. If you do the calculations, 35 millilitres of liquid nitrogen, that's 7 medicine spoon loads, and you let it all boil at normal room conditions, it goes from 35 millilitres to 24,000 millilitres. That's 24 litres in cookery speak. There is a huge amount of empty space in a gas compared with a liquid. But you know that already, because you know if you go for a run, you can knock the air particles around you as you run. You don't leave a trench of nothing behind you. The particles have to go around you. That's not too difficult. You get up to your neck in a liquid like water at the beach or at the swimming pool and try running. You can't. In a liquid, there are so many more particles close together, you don't have the energy to push them around you as quickly. Let's leave nitrogen and let's concentrate on the second biggest gas in the air. Let's concentrate on the gas oxygen. 1 breath out of every 5 on average is oxygen. It's also colourless, it's odourless, and it's tasteless. Oxygen is needed for us to breathe. It's also needed for us to do this experiment. Strictly, of course, we don't need oxygen to breathe. We need oxygen to stay alive, and the process is more correctly called respiration. Breathing is passing any gas into and out of your body. It's what happens to the oxygen that keeps us alive. And as I said, that's respiration. But it also causes other chemical changes. Let's leave them to one side. Where does all the oxygen on planet Earth come from? If we examine the atmospheres of the other planets in our solar system, this planet is the only planet with oxygen. It happens to be the only planet with plants. Plants make oxygen. Some of you may have studied this already. Plants take in carbon dioxide and water from the air and the soil, and they use the energy of the sun to turn it into oxygen. Now, strictly, that process, and some of you will have heard of that process as being called photosynthesis, that process is not there to make oxygen. That process is to turn the energy of the sun into simple sugars. And it stores the energy of the sun as a chemical, as simple sugar. The oxygen is the waste product of that reaction. We as human beings, we as animals, need that oxygen to stay alive. We live on a plant's waste product. Now, bearing that in mind, let's consider this. Plants are brilliant scientists. They're brilliant chemists. I cannot make oxygen the way plants do. I've been studying chemistry for 40 years. Probably longer than that, by 50 years probably. And I cannot produce oxygen the way plants do. They're far too clever. I can make oxygen, but not the way plants do. I'm going to do it here. It's a bit messy, so I'm going to use my most exquisite tablecloth available at most supermarkets. And I'm going to do the experiment here in this bowl, but in this measuring cylinder which I'm placing in the bowl. And my starting material, I'm going to use this solution. This stuff looks like water. Water, as a lot of you will know, is made up of 2 parts hydrogen, 1 part oxygen. That's why it has the chemical formula H2O. 2 hydrogens and an oxygen. This stuff, this chemical, contains an extra oxygen chemically attached to a water molecule. So it's no longer H2O, it's H2O2. And that extra oxygen does not want to stay attached. It wants to break off, it wants to decompose or dissociate. Now it might be hard for you to see the fact I've got 200 millilitres of this chemical called hydrogen peroxide in this clear glass measuring cylinder, so I'm going to add a bit of food colouring to make it easier to see. Food colouring doesn't interfere with the piece of chemistry I want to show you. 200 mils, about 10 pounds worth of that chemical. And I want to break it down into oxygen. You probably can't see whether there's any oxygen being produced in there. We can't see any bubbles. So we'll make it easier for you. We'll add some washing up liquid. Now a good squirt of best washing up liquid. And I'll give it a mix so that the washing up liquid doesn't just sit on the top. And we'll see if we can trap the oxygen gas as bubbles. Well, there are a few bubbles in there, but that's probably come from the fact I've been swirling this to mix it. The reaction is very slow. We probably have to wait all week for it to fill up the measuring cylinder with some bubbles in it, unless I speed it up the reaction. And that's what I intend to do here. I'm going to use a piece of chemistry that you'll learn about when you're probably in year 10 or 11 of your secondary school. So I'm going to use a chemical called a catalyst to speed up the reaction. There are lots of catalysts. This particular one will speed up this reaction, releasing oxygen. Risk assessment, I shouldn't have this chemical in contact with my bare skin if I think I'm pregnant. I'm not pregnant, so I'm just happy to have it in here. Otherwise I'd have to get some gloves on. Let's see if we can make a bit of oxygen more quickly. And there we are, loads of oxygen foam. Remember, the oxygen was being produced from the hydrogen peroxide solution. I broke it down into water and to oxygen, and the washing up liquid simply trapped it. Now I really want to stick my fingers into that lot, but I daren't, because I know that foam is over 100 degrees centigrade. A huge amount of heat energy comes out in that piece of reaction. If I stick my fingers in, I get a heat burn because it's so hot. I'd also get a chemical burn because there's unreacted chemicals in there. It's some of you might be able to see on your screen, there's some white stuff coming off the top there. And I bet a number of you are thinking, oh, that must be steam. Well, you would be wrong if you thought it was steam. Steam cannot be seen. I know what you're thinking. When I was taken into a kitchen, I even got taken into a kitchen by my mum and said, don't touch that kettle, don't touch that pan of boiling water. That white stuff coming off the top is hot. That white stuff is called steam. Well, yeah, the white stuff is hot that's coming off, but it isn't steam. If you watch a kettle boil, and I'm sure some of you have done this, and you look at the spout, there's about a 3 to 4 centimetres gap above the spout where you can't see anything. Now, if steam happened to be white and it's formed inside the kettle, how does it come through the spout without you noticing? And the answer is this: the steam is the colourless stuff above the spout. And when the steam cools down in the cooler air of your kitchen, it condenses into billions of droplets of liquid water or condensed water vapour. The same as in the cloud, the same as what you make when you blow your water-laden breath into liquid nitrogen. The only difference is this was hot condensed water vapour, and with the liquid nitrogen it's cold condensed water vapour. Now I need to get rid of this out of the way, so I'm going to ask my colleague here, Dr. Johnny First, to come and move this out of the way. You can see he's got gloves on so he doesn't get burnt from the chemicals or the heat, and he's going to wrap that out of the way, and we'll give it to one of our students to clean up later. So that's oxygen production, but what else do we need oxygen for? We need it to stay alive. We talked about respiration, but we also need oxygen to allow things to burn. So let's burn some material. Because I'm in the lecture theatre of the University of Bristol, I don't need to burn a piece of paper or a piece of stick. I can burn something far more exotic. I've brought with me the fuel for drag racing cars. And I've also brought with me not a test tube, one of those fancy water bottles that you get in some offices and even school staff rooms. The chemical I've got in here is the fuel for drag racing cars. It's not petrol, it's not diesel, it's one of these fancy biofuels. Now, I'm going to put in a small amount of the methanol into the container. I'm going to put the lid on and put that out of the way. And I'm going to shake up the fuel. Many people don't realise that liquids don't burn. Liquid petrol doesn't burn, liquid diesel doesn't burn. It's not the liquid that burns. It's the vapour that exists above the liquid. And that's what's mixing with the oxygen in the air in order to react. Now I'm shaking this up very, very carefully so it doesn't touch my skin. This particular chemical causes death. It's highly toxic. It will pass through your skin into your blood supply, causing irreversible brain damage and death. So you've got to know what you're doing with chemicals. I'm draining out the surplus liquid. So the container now only contains air, and it's the oxygen in the air we're interested in, and some of the liquid that's turned to vapour. We've vaporised it, we've evaporated it. So what I have in here is now a fuel-air mixture, and fuel-air mixtures are explosive. And what we're going to do is put a flame in so that you can examine the colour of the flame that comes out. And then we'll talk about flame colour. Now once I've got myself ready, we'll actually turn the lights out, because this is best seen in the dark. And I will take a spill and put it into the top of the bottle. Watch to see the colour of the flame that goes in and the colour of the flame that goes out. Okay, stop reacting and put the lights back on. Flame colour is incredibly important. Yellow flames are very hot. Blue flames that came out of the mouth of this water bottle are very, very, very hot. Blue flames liberate more heat energy than yellow flames. Yellow flames, we say, are formed by incomplete combustion. Not all the energy that's available is being released. Blue flames are complete combustion, and all the energy from our fuel-air mixture has been released. Now in a car engine, in a traditional fossil fuel, petrol or diesel car engine, the energy to come to drive the car is formed when the fuels are burnt in the combustion engine. When you burn fuels, two chemicals come out. One is carbon dioxide, colourless gas we can't see, and we'll look at carbon dioxide in a moment. The second is this stuff. You saw me empty the container earlier. When you burn a fuel, you produce water. Most fuels are made from carbon and hydrogen compounds. The carbon becomes carbon dioxide, the hydrogen adds oxygen to it, becoming H2O, water. Now let's have a look at some carbon dioxide. I've got some here. In fact, I've got a big box of carbon dioxide. Now you might think, stupid person, fancy putting carbon dioxide gas in a box. Well, I didn't say I had carbon dioxide gas in a box, I said I had carbon dioxide. I brought with me the solid version of carbon dioxide. It looks like ice. There is absolutely no water present, so its nickname is dry ice. Dry ice is at least minus 78 degrees centigrade. And if I was going to touch this for more than a split second on any part of my skin, I would need to wear gloves because it will cause frostbite. Frostbite destroys your flesh, and if you don't have your dead flesh then cut away with a surgeon with a very sharp knife, you'll end up with a disease called gangrene, which can kill the rest of you. You have to know what you're doing when you handle chemicals. And what I want to show you is just a couple of experiments, maybe 3 experiments with the dry ice. The first, I want to show you what happens when you warm up dry ice. I've got here another of these rubber gloves. let's put a bit of dry ice into the glove. Now it's the same rubber as in a rubber balloon, so let me just knot up this glove, and I've effectively made a 5-digit balloon. So I've got some dry ice in the fingers. I'm going to put the heat energy out of my hand into the dry ice. My hand is getting cold because I'm losing my heat energy. I'm giving my heat into the dry ice. I'm not getting cold from the dry ice. I'm getting cold because I'm losing my heat. You can only move heat. You can't move cold in that way. You know, when your parents say, shut the door, you're letting the cold in, say, no, I'm not, I'm letting the heat out. You'd be correct. What you can see there is, I've made a cow's udder. This is gas in the top. Listen. That's solid in contact with gas. That's a little unusual. There's no liquid. I've not melted the dry ice. If I melt the dry ice, I make liquid carbon dioxide. Dry ice is one of the few compounds that goes from a solid straight through to a gas without becoming a liquid. And we call that change subliming or a sublimation. And that's a weird property. There aren't many chemicals that do that. Maybe because you understand that, you'll now understand this. There is an old frying pan, just one that's no longer in use in my kitchen. Let's put a few pieces of dry ice on this hard wooden bench and put the frying pan on the top and see or observe what happens. It's a singing frying pan. Why does that happen? Well, I'm not going to tell you. Most research is done in a library. Look it up. One last experiment with dry ice. I need a few other materials for this. I need a big beaker and some tap water. In fact, I'm going to stand this onto a white mat to make it easier for you to see. Now that is tap water. This is a chemical indicator here. And if that is tap water, when I add this orange, it should go green. So there we are. Now I don't like green, I'd rather purple to start with. And this is chemistry, not an art class. So I'm going to make this slightly alkaline by adding this chemical, just a touch, and you can see we're now ready to start. I'm not going to explain why it does that, but it simply does. Your year 7 and 8 teachers in secondary school will explain why that happens. So we've got a purple solution, and in a moment I'm going to add a handful of dry ice into that solution, and I want you to make observations. Don't just see one or two things and turn to your mate and say, did you see it go green with purple stripes? You might miss a whole pile of other observations. I'll tell you when the reaction is finished, when to stop observing, and then we'll go through and check how many you actually got. Now I had to blow some of the cloud out of the way for you to observe this more clearly. I'll let this run another 20 seconds or so because there's one more colour change to observe. Okay, I think we can stop observing. Right. Let's see how many observations that you can make. If you're going to end up being a scientist, an engineer, a medic or a technologist, you're going to need some great observational skills. So let's check on what they are. First thing, dry ice sinks in water. Water ice, of course, floats. Otherwise icebergs don't work. You've seen that observation when you put ice cubes into your Coca-Cola or lemonade. So dry ice sinks. I can see gas bubbles in the liquid. That's an observation. I can see a foam on top of the liquid. That's an observation. I've noticed that the foam has taken up some of the same colour as the liquid. That's one that's slightly trickier to see. I can see cloud forming. I've noticed the cloud is white. I've even noticed that the cloud falls down the side of the container. That's 7 observations so far. And I haven't even talked about the colour change in the bottom. For those who were looking carefully, it went from purple to blue. Blue became green. Green went yellow, and that yellow has now turned orange. That's a total of 11 observations. And if you stand a chance of being a scientist, technologist, engineer, or medic, you need to be good at observations. You need to actually get at least 7 out of 11. And if you didn't practice your observations, it's an important skill. Right, I've nearly come to the end now. I want to do to you what your teachers do. Your teachers are probably of the type that will tell you something at the start of a 1-hour lesson, and they expect you to remember what they told you an hour later. Well, this is nearly an hour later. I've got some more blues. You know the names of 2 gases that are lighter than air, that are low density gases that will make balloons float. You know what I've got to do to test for those gases, and you know what the outcome is for each. So all I need to do is to do the test. See if you can remember what these mean. I think we'll do one with a light on and one with a light off. Let's see what's in this one over here. So hopefully you've remembered what that is. And we'll do the second one, which is the same gas as the first one, with the light off. Both of those, of course, were hydrogen gas. Thank you for your attention. I hope you've learnt lots watching this video. If you've got any questions, you can either ask your teacher or ask your teacher to email us at the University of Bristol. Bye.